Okay, folks, chemists, and everybody else who is joining us today. This is Chemistry 132B, and it's part of the Physical Chemistry series. Most of you will be in your senior year, but hopefully we'll have a couple of juniors as well. So this course is called Quantum Principles. Okay, so we will be talking about the quantum mechanics of chemistry. So some of you may wonder, why do I need to know this and why do I have to take this course? Because I hear very bad stories about this course. It's too hard, too much mathematics in it. I don't want to do it. Okay, so well, the answer is that this course apparently is useful for you in order to appreciate really the underpinnings of chemistry and understanding why things are the way they are. So in many cases, many of you will be interested in synthetic chemistry or material chemistry, really the practical side of things. And quantum mechanics is offering explanations on why things work and other things don't work. Okay, so for instance, why can a certain bond be formed while another bond cannot? Why is this bond stable, the other one is not? Why does this atom behave like such and the other one like so? So these are important questions. And even though maybe on a daily basis, if you are standing in front of the hood, making your molecules, you don't really think about these things. But it turns out that it is actually important in order to understand and also predict why certain molecules exist and other molecules do not. Okay, so we'll be doing that this quarter, and we'll be starting slowly as usual, but we'll be building it up. And it is true that there is a fair amount of mathematics in this course, but the emphasis is not on the math. Okay, so you don't have to be a math expert. And the steps that we will be taking to solve some problems hopefully are evident. Okay, so we'll be providing you with all the tools that you need to solve such problems. It's definitely not about the math, but sometimes we just need to do a certain calculation to figure things out. So that's just part and parcel of physical chemistry. So hopefully not too much struggle for you guys in this course, and hopefully you come to appreciate why the physical explanations that we will be providing are actually fun and extremely useful. So it'll make you a better scientist in the end. I hope. That's my hope. Okay. So I am Eric Potma. Okay. So I'll be your host, your humble host this quarter. And I'm not by myself. I am part of a teaching team. We have two more people that help out. We have Ahmed, who is a TA, teaching assistant. I'm not sure if he is actually on the call today, but in any case, he has office hours and of course does discussion sections, so please check that out. And we have Yingting, who is on the call today. So hello Yingting, how are you doing? And she is also
I'm good.
And she'll be helping you out with the discussion sections. So let me first dive into the logistics of this course a little bit, so we get that out of the way. So hopefully then it's clear. And then we just actually start talking about quantum mechanics, okay? So the first thing is to have a look at the class website. Hopefully you can see my screen here. This is currently what it looks like. It's very sparse, but we will be populating the website with a lot of items as we go during the quarter. Okay, so here's the syllabus. If you click on it, you can see the rough flow of the quarter. So we'll be talking about the basics of quantum mechanics first, then wave functions, translational, vibrational, rotational motions. It's all standard parts that we have to cover, but it's actually really interesting stuff. So, and then we move into atomic wave functions. Okay, so atomic wave functions, of course, is where really the chemistry is going to hit, because you're going to see how we can explain properties of atoms. Some of you may have already heard about many of these things I'll be talking about, but we really will be looking at the nitty-gritty a little bit more and try to find justifications for why things are the way they are. We'll talk about angular momentum and the spectra of atoms, then many electron atoms, so basically orbitals, and how we can explain that they have certain forms and certain energies. We'll talk about valence bond theory and molecular orbital theory. And then we'll, in the end, this is a very interesting week 10, we're going to talk about polyatomic molecules, basically Huckel theory of pi conjugated systems, very interesting topic. That I'm sure if you are a real chemist, you will enjoy very much. So that is the general menu of this quarter, and we will be going through it, and we will have plenty of time. We'll not be cramped for time. I have allowed plenty of buffers in here to make sure that we can cover things conveniently without rushing through. This is the division of the grading, basically the grading scale. We have homework to do. Every week, there is a homework assignment due. We can call them quizzes, homework quizzes, and they're 15% of your grade. Then we have what I call quizzes, and those are really midterms. Okay, so we have 2 midterms, 25% each, and then the final exam is 35%. So that's kind of like the overall division, and hopefully that's a fair distribution. Homework is an important part, of course. It will be done online, okay? So it'll be done in Canvas. I'll show you in a minute how to do it. And it is the way to make sure that you are staying with the program, okay? Because we have to do some exercises, some problems in order to digest all the material of this quarter. The midterms will be held twice, so we have 2 midterms, and I'll be telling you when as we get there. I think it's going to be week 4 and week 8. It's a 1-hour quiz, if you wish, and we'll be doing it during the lecture hour. Okay, so it's just 1-hour quiz. It's a time quiz, so it's a synchronized quiz. You have to do it at a certain time and complete it within a certain time limit. This is me, Eric Potma, and I have office hours on Fridays from 1 to 2. So if you want to join me and ask questions about anything that has to do with the course, you can click on this room here. I'll be there, and please join us, because it's going to be very useful to bring your questions to the table and talk about it. Ahmad is doing TA discussion sections, but he also has office hours, as you can see. So, and that's going to be on Thursdays at 12. And Yinting, I think, is also. Are you doing office hours, Yinting?
Yeah, but I was going to wait for people to take a poll later on to see when I should have it.
Okay, very good. So there's going to be another office hours in addition to discussion sections, which of course are the place for you to practice some problems. Every week there will be discussion section, and we have a worksheet with questions, and we'll be trying to solve those questions. So please join us for these discussions, because again, it's a great place to get some good practice. There's a couple of documents here, as you can see, quotes by founding fathers. That's really kind of for fun. It's like some background material about quantum mechanics. So you can read it at your leisure if you're interested. And then the second document is called Basic Mathematical Tools in Quantum Mechanics. And that is useful because there's a couple of tricks and integrals and so forth that we will be using during the quarter. And they are explained on the document, how to solve those problems, how to solve those integrals and so forth. So please have a look at that. In many cases, people forget about this, and then they can solve an integral, but the answers are basically given on this sheet. So please don't forget, you can consult it at any time. Okay, so the flow is a weekly flow. So we have week 1, that's where we are right now. And we are looking at lecture 1. So lecture 1, the lecture notes are already posted. I typed them out, and you can just read that. And it's basically a summary of everything that I'm talking about during the lecture. This is the worksheet. The worksheet will be discussed in discussion section. Okay, so this is the question, a couple of questions that we will be solving during discussion. And then this is the quiz. That's basically the homework. Okay, so the homework for week 1 is called quiz week 1. And if you click that, then you can do that at your leisure. But you have to complete it by midnight on January 10th, which is on Sunday. So every Sunday at the end of the week, before the beginning of the next week, the homework is due. Okay, so, and that's basically a weekly thing. So every Sunday at midnight, the homework is due. Okay, is there any questions about these general logistics of the course? Anything that's not clear? I guess I have to say something about the book. We have a book, which is the Atkins book. Let me show it to you what it looks like. This is the book, okay? Physical Chemistry by Atkins. And we'll be discussing a couple of chapters in the book. I'm using the book as a reference, okay? So it's a good book, I think. It's appropriate for this level. And you can consult it and read up on some of the segments that we will be talking about. But I will not be using the book as the main source. Okay, so all the material for this lecture and for this course is going to be presented during lecture and during discussion. Okay, so that basically is the main core, the main material of this class. So make sure you understand that. The book is for reference. We will not be covering everything in the book. And we'll be covering some things that are not in the book. So that's why the primary source of material is really the lecture material. Okay, so.
I have a question about your office hours. Sorry to interrupt.
Go ahead.
So I have a time conflict actually. I have a lecture during your office hours. I think the other TA is fine. I know we don't know about evenings yet. Are you gonna plan on changing those if there are other conflicts, or are you gonna be keeping that time for Friday?
If there are a lot of people who have conflicts, then it is prudent for me to change it. So yeah, people should let me know. If the majority of the class can make it, then it makes no sense for me to have those office hours at that time. So so yeah, let me know if there's enough pushback. I'll move it.
I have a question too. Are exams open notes?
Yeah, they are open note, they're open book. So you can have any notes during the exams, basically the midterms and the final, and also the homework, of course. But during the exams, the timed exams, we will be doing the lockdown browser. So you cannot really browse for information. So also, you shouldn't be calling your friends on the phone and things like that. Like, hey, what answer do you have for question 3? So that's something, of course, we don't want. That's why we use these additional tools. I think you've seen it before, but we'll be using the same tricks.
Thank you.
Mm-hmm. There was also a question in the chat about the quizzes. Are they midterms? Yes, they are the midterms. I'll change the wording because it's maybe a little confusing. I think the word quiz is cuter. It sounds less, dangerous and threatening. So that's why I call it quizzes. But really, those are midterms, and there's 2 of them. Okay. Another question. So we should print out our notes instead of have them digitally, since respondents is being used. Yes, if you think you'll need the notes during your exam, then you should print them out. Okay, so you can have any written documents in front of you. You just cannot use your browser to look things up on Wikipedia or anything else. Sometimes questions are found online. Typical questions can be found online, and the answers are given. Of course, that defeats the purpose, and that's why we have the lockdown browser in there. Okay, pretty good. Let me start by saying the following. Like I said, the course is called Quantum Principles, and the main reason why we have to cover this material is because it forms the foundation of molecular and atomic properties. And I think many of you are familiar with some of the ingredients of quantum mechanics and why it is important for chemistry, but you may not really have this cohesive picture in your mind of how everything works and where it came from. And so that's one of the the purposes of this course, to make sure that you understand where it's coming from and to understand why it works. So the story starts many years ago, and if you open up a textbook about quantum mechanics or quantum chemistry, then most textbooks start in exactly the same way. They basically say that 100 years ago, 200 years ago, people had a pretty good idea of how to describe the motion of particles. Of course, this is called Newtonian mechanics, Newtonian classical mechanics. And these ideas that Newton basically came up with were further developed. And at the end of the 19th century, so by the end of the 1880s, 1890s, people had a pretty good grasp and a good mathematical framework that could explain basically the motion of any particle of relevance that they were familiar with, right? So if you throw a stone, you can exactly predict and calculate where that stone will land. Or if you shoot an arrow, you can exactly predict where that thing will go. And those tricks were available to people at the time already. And that seemed like a pretty complete theory. The theory of the motion of particles was considered complete in a way. On the other hand, there was, of course, electromagnetic radiation that people were very familiar with at the end of the 19th century. The equations of Maxwell's equations, were known, and they described basically every property that there was to know about electromagnetic radiation. And so these two ingredients, the properties of matter and the behavior of electromagnetic radiation, together is called kind of the classical framework of the classical physical framework. And it was considered to be, this is maybe all there is to know, and this is considered maybe an endpoint in the development of classical physics. Of course, there were some outstanding questions, and this is where the books typically start. They have a couple of observations that people had that couldn't explain with the existing framework, and we can basically separate these problems into two parts. Okay, so the first part is really the issue with matter. Okay, so matter is this is really hard to write. Matter. Wow. So there was a couple of issues there, and one of the issues was the issue of the heat capacity, which could not be explained well, and another issue was the spectra of atoms. Okay, so I will not go into details because I think it's kind of like it's a long story, it's an interesting story, but it doesn't really add too much to our course. I think the only thing we should know is that there were problems. Okay? There were problems with heat capacity, and there were problems with understanding the spectra that came from atoms. Now, what does that mean, the spectra that came from atoms? That simply means that if you have, let's say, an atomic gas, let's say helium or hydrogen, and you illuminate it, then some radiation will come off, some emission will come off. And this emission was known to be very discrete, meaning that only a couple of wavelengths were emitted. And that is something that it could simply not explain with the current framework that they had, the framework that they had at the time. So there were some problems, okay? So we can call it the heat capacity, this is new to me, this pad that I'm using. It's really hard. And the second one was, the problems of atomic spectra. And both problems simply people couldn't solve, and they were scratching their heads what to do about it. And it was forming a motivation for alternative theories. Now, on the other hand, we had radiation. Actually, I'm getting better at it now. So radiation, of course, is, we know what radiation is. And there were a couple of observations that also were not really fitting with classical mechanics and classical physics. And one of these was the black body radiation. Black body radiation. Basically, that is the radiation, the spectrum that comes off a so-called black body. That is basically an enclosed body that is black, means that it basically absorbs all the wavelengths and then re-radiates. So let's say if you warm up such an object, then it radiates wavelengths according to its heat. That's called black body radiation. Again, we're not going to go into the details, but it is useful to know that an observation like that simply could not be explained with classical mechanics and classical physics. Another issue is the so-called photoelectric effect. And this is something that is famous because Einstein was involved with this. Photoelectric effect. Ooh. Looks nothing like my handwriting. Photoelectric effect is another observation that people had. And what it is basically you illuminate a metal, for instance, a metallic surface with light, and then you crank up the amount of light that is impinging on the surface until some of the electrons from the surface will be ejected. Okay, so you're basically trying to eject electrons from the metal through radiation. And this is a well-known effect, but the interesting thing was that if you have the wrong wavelength, then it doesn't matter how much of the light you send onto the metal, there were simply no electrons coming off. Well, if you have another wavelength, let's say the right wavelength, then you could just send as little as you wanted, and you could see electrons. Okay, so at very low levels of light, there would be electrons coming out. And that was a very strange observation, because it basically said it doesn't matter how much energy you send onto the surface. The electrons only come out when there's a certain match between the energy of a wavelength associated with a wavelength and the energy that the electron needs to get out. Okay, and the energy the electron needs to escape from the metal. And so these effects were inexplicable in the old framework, and they form the basis of the foundation and motivation for quantum mechanics. Okay. So quantum mechanics is an interesting theory because it developed over numerous years. This was not something that happened within a week or a year or so by one person, but it developed over many years by many people. Okay, so this is very unlike Newtonian mechanics, for instance, where you have Isaac Newton, who basically for 2 years during the plague, he sits at home and he writes down his entire, dissertation and book about Newtonian mechanics, right? So it's developed by one person over the time span of only maybe 1 or 2 years, and that is a complete theory. So this is a very different story. This is basically a whole team of people who were not necessarily affiliated from different countries who, were trying to attack these problems above and came up with solutions that then converged and morphed into what we now know as quantum mechanics. So it developed over a time span of numerous decades, in fact, before it was considered complete. So it's a different kind of theory. And the word quantum is in there, and that is maybe strange. What does that mean, quantum? And we'll see what that means as we go. But the bottom line is that the mechanics or the motion of particles, in this case, for our purposes, it's the electrons that matter. The quantum means that the electron shows quantized behavior of its properties. So let's take, for instance, the property of energy. An electron has a certain amount of energy. The word quantum means that the electron can only have certain amounts of energy and not other amounts of energy. Okay, so it's quantized. You can only have this much energy, but not anything in between. Okay, so that is strange. There's nothing in classical mechanics that says that it has to be so, and therefore you need something else, a new theory, and that's called quantum mechanics. Okay, so we'll see how that works. So let's start with the problem of radiation. Okay, and what people came up with and realized as they studied this problem. So the problem was that the issue of black body radiation and photoelectric effect could not be explained by the classical framework. The classical framework, if you think about light, consider basically light to be a wave, okay? And this is something that you all know, right? And the wave, of course, is described by lambda. That's the wavelength. And then the wavelength is related to the speed of light over frequency, okay? So this nu here is the frequency, c is the speed of light, lambda is the wavelength. So we all know that, of course. And the classical framework says if you have a light wave, then this light wave, the strength of this light wave is indicated by its amplitude. And this amplitude could have any value. So if you have a very little light, then the amplitude of the wave is very small. And if you have a lot of light, very bright light, then the amplitude of the wave is very high, okay? And so there is no limit, there's no quantization of that amplitude. The amplitude can have any value, okay? So there's nothing in classical mechanics that says that you can only have certain values. Now, one of the great breakthroughs that Einstein had in 1905 is that he says, well, the energy, which is of course, another word for the amplitude of the wave, is not just any value. It is in fact a constant, and that's a constant of Planck times nu. Okay, nu is of course a frequency. That's the same as the frequency right here. Okay, it's the same nu, but this h is a new quantity that was basically gaining prominence. H is of course a constant of Planck. Okay, and it's a very small value, and this is important. There it is, minus 34 joule times second. Okay, that is the value. It's very small. So 10 to the minus 34 is, by all means, is a small value. It's joules per second. So, think about the quantity of joules. Okay, I think most people are familiar with joules. 10 to the minus 34 joules times second is a very small quantity. And that means that quantum mechanical effects, in fact, are very small effects. In this case, they are manifest only at very low energy levels. So look at this. The smallest energy that a wave can have is this. Okay, it depends basically on its frequency times this constant of Planck. Okay, so if you have light of a certain frequency, aka a certain wavelength, let's say you have red light. Okay, let's say you have red light, which is about 632 nanometers. It's beautiful red. You can calculate the frequency of that, and then multiply it by h, and it says that that is the minimum amplitude or energy that that color can have. Okay, so what does that mean, minimum energy? Well, that means that you cannot have an amplitude that is less than this if you have that frequency of light. So this amount here is what we call photon. Okay, that's the photon energy. So that is what we understand as a light particle. It's the carrier of energy of electromagnetic radiation. You give it a name, it's called photon, and it means if the photon has a certain color, then that is the energy of the photon. All right, and if you have two photons, then it's twice. Okay, so that means I can put an n in front of here. That is the number of photons. So if I have 1,000 photons, then it's 1,000 times this energy contribution, leading to a total energy that is 1,000 times the original photon energy. But this is quantized, as you can see, because this is an integer value. Okay, so there's nothing in between. There's not 2.5 photons. There's only 1, 2, 3, 4, 5, 6, not 4.5, not 4.32. Okay, so only integer values, and therefore the energy of electromagnetic radiation is quantized. Okay, so here's the first word of quantum that comes into play. The energy of electromagnetic radiation is quantized, and that was a very important realization in 1905. Before that time, people did not fully appreciate that. They understood light as something that is continuous, certainly not something that is discrete and quantized in terms of its energy. So that was a very important realization. I think most of you have heard about this in several ways, but please understand that it is a very remarkable conclusion that people drew in those days, that the energy is quantized. Okay, so that's the first clue that we have here. Now, what does it mean exactly, and how can we understand the implications of this? Now, let me show you the following. Let's see if we can switch here to this. Okay. So here's the picture, and most of you have seen the picture, a picture like this. And what you see here at the bottom is light coming in. Those straight lines means that the light behaves like a so-called plane wave. Okay, and then there's two holes in the screen, and then after the holes, we see this interference pattern. Okay, so this is something that we all know. This is called the diffraction of light, and it is it's a direct consequence of the fact that light has wave-like properties. Okay, because it behaves like a wave, it diffracts onto itself, and you create these beautiful fringes. Now, if you put a screen anywhere here, okay, anywhere on this side, then we see, of course, those fringes very clearly. So that's basically shown here. Let's look at the picture here on the top, on the left top, and you see this beautiful fringing. That basically is a result of having two holes in the screen. Okay, so just another way of saying the same thing. Now, this is, of course, nothing new, and you can do this experiment at home. And it was done, 150 years ago by Thomson. He proved that this is happening, and therefore that light behaves like a wave. But what is interesting for us is to ask the following question: what happens if I turn the lamp, okay, or the light source down in energy? Okay, well then, of course, the pattern is going to be more fuzzy. Okay, it's going to be dimmer. Okay, so let's say here on the right, it grows dim. But then I turn it down even more, so it becomes even dimmer, of course, but it becomes a little bit more grainier, and then you see individual specks on the detector screen. What does that mean? Well, each speck can be understood that light is interacting with a pixel on the camera. Okay, so this energy is exchanged between the light field and a pixel on the camera. Okay, so we can understand that if it happens, and we know that light can only be partitioned into the energies of a photon. So that means that a photon energy has been exchanged between a pixel on the camera and the light field. All right. So that's a successful photon detection event. Right. So this is the weakest pixel intensity is basically detection of a single photon. Okay. So that's one interesting thing. That is kind of a quantum mechanical manifestation, because the light field can only exchange energy with the camera in fixed amounts, namely photon energies. Now that's fine, but what is interesting is the following. Okay, so we have here locations where the camera says, okay, I saw something, right? But if you look carefully, you can still see this fringing pattern, meaning that in the locations where the fringes were very bright, there's a higher chance that a single photon event will be detected. And if you lower down even more, you see some specks, okay, all the way here on the right. That may not seem like much, but if you look carefully, it is still having this pattern. Now, you may not think much of this, but this is utterly remarkable if you think about it a little deeper, because it means that if I have only one photon that is detected on the camera, let's say the photon over here, okay, that photon arrives in a place that overlaps with one of these bright fringes. You will not find this bright spot in the dim part, or at least with a very low probability. That is kind of strange, because if that photon basically went through one of the holes or two holes at the same time, it must have sensed the presence of the two holes. Okay, so we have one photon, so one carrier of photonic energy, of electromagnetic energy, photon energy, and that photon must have gone through the two holes to arrive in one of the bright spots, because the bright spots are a direct consequence of having two holes there. If I have only one hole, I get just a beautiful diffuse pattern, no stripes. The stripes are a direct consequence of having two holes. Yet I detect only one event. So the photon is therefore a wave that has a fixed amount of energy, but that fixed amount of energy can sense the two holes. Okay, so this is something that people were utterly amazed by, and still are in a way. So on the one hand, of course, we have the quantization of energy, so there's a fixed amount of energy, but there's no fixed location of where that energy sits. In fact, that energy can go through two holes at the same time and interfere with itself. Okay, so that is a peculiar property of photons. Okay, and so this is actually one of the purely quantum mechanical manifestations of light, where light is truly a quantum mechanical wave that can sample two locations at the same time, right? While it has a fixed energy. So it behaves like a particle, but it also behaves like a wave, right? So this is the famous wave-particle duality. I like this example a lot because, sometimes if you see this diffraction of light, you say, okay, that's great. There's in principle nothing quantum mechanical about this picture, but the last picture here is quantum mechanical because it says that even though there's discrete energies, it can still sample two locations in space at the same time. Right. So that is basically a quantum mechanical manifestation of light. Light is quantized in energy, yet it behaves like a wave that can be in certain locations at the same time. So it is spatially delocalized while it is localized in energy space. And energy space is localized in this case, and it is delocalized in space. Okay. Okay. So that is, what people figured out about light. But there is another aspect, of course, and that is matter. And in case of matter, you know probably already that Louis de Broglie made a very important contribution. Okay, and he says, these properties of light are very interesting. I wonder if there is a symmetry between radiation and the properties of matter, and that turned out to be the case. Okay, so what he found is that indeed we can think about matter as having a wavelength. Okay, and that is of course the Broglie wavelength. That is h, that's the same h divided by p, where p is the momentum. Okay, so it's h divided by m times v, where v is not nu, that's a v, that's velocity. Okay, so this is basically assigning a wavelength to matter. Okay, you see here, this is m. A photon has no mass, but matter has mass. Okay, it has an actual mass to it. An electron is matter because it has a mass. If the electron has a velocity, it has a momentum, and h over momentum assigns a wavelength to matter, to an electron. Now, what does that mean? Well, that means that, of course, like light, electrons can diffract. Okay, so they can show interference phenomena. So that is well known, and let me show you another example here. There it is. Here, this is a pattern. It looks very similar to the pattern that we saw before. However, there's an important difference, and that is this pattern is caused by electrons, so by matter. Okay, so unlike the previous example where we had light, which is massless, here we have an actual piece of matter like electrons that went through two holes and have exactly the same interference pattern. And the same issue holds. If you send one electron through these holes, then it forms also an interference pattern. So like a light wave, an electron, which is very hard for us to understand because it carries mass, an electron can sense two holes at the same time. So like light, an electron can be delocalized in space, yet localized in energy space. Okay, so the energies in energy space, it is actually localized, but in real space, it is delocalized. So I have a quick little quiz here. This is just for fun. This is not for any grade or anything. Okay, so I'm going to launch this poll because just to kind of like make sure that we understand what we're talking about. Okay, so just give yourself 1 minute and click what you think is the correct statement here. So it compares the properties of electrons with the properties of photons. They have very similar properties, it turns out, but there's also some differences. So that's what this question is about. All right, very good. I'm going to close it. All right, so let's go through this. Option A, like photons, electrons are massless particles. That is not true because electrons do have mass. Okay, it's one of the defining characteristics. Photons have no rest mass. Okay, so they are definitely different from electrons. Photons and electrons are not the same things. Electrons have mass, photons have not. Like photons, electrons behave like waves. That's true, and travel at the speed of light. That is not quite true, unfortunately, because they can travel at the speed of light, even though it's really hard to make them do that. But the m times v, where v is the velocity does not have to be the speed of light. It can be a velocity that's much smaller than the speed of light, and in almost all cases, it is. Okay? It's really hard to make matter go at the speed of light. This velocity of an electron is always less, typically always less than the speed of light. So B is also not correct. C, because electrons have mass, they can be described as waves. Well, they certainly can be described as waves. That's what the Broglie says, but that's not because they have mass, okay? Because as we know, electromagnetic radiation is also behaving like waves, and it has no mass. So mass is not a necessity for it to behave like a wave. Option D, the wave-like properties of electrons depend on their speed, but not on their mass. That is incorrect, because the Broglie wavelength is h over m times v. So m is, of course, the mass, but v is speed. So it depends on both. So the only right answer is none of the above. So all of them are actually wrong. They have something right about them, but they also have something wrong about them. So none of them is basically correct.
Professor, could you
Yeah.
explain option C one more time, please?
Yes. Option C says because electrons have mass, they can be described as waves. This is not true because the fact that they can be described as waves is not implicit on them having mass, okay? Because, like I said, photons can also be described as waves. Photons have no mass. So you don't need to have mass to have wave-like properties, okay? But it's true that even if you have mass, you can be described like a wave, but it's not a necessity, okay? So you don't, mass is not a necessity for it to be described like a wave.
Thank you. I got it.
Say again?
Would it be the same case for D then? Like it can be described as, it can have wave-like properties, but it also doesn't depend on their speed. Similar.
No, that's different. Option D is different because the wave-like properties do depend on speed and mass. Okay, so electrons, the wave-like properties of electrons is the wavelength, lambda equals h, constant of Planck, over m times v. So it depends definitely explicitly on m and v. Okay, so if the speed is a little different, then the wave-like properties will be a little different. Okay, so it definitely depends on m and v at the same time. So
Okay.
D is wrong for a different reason that C is wrong.
Thank you.
All right. Okay, so why is that all important for us? If electrons, let's say, have wave-like properties, why is that relevant for us? Well, it is relevant because if I look at the magnitude of the wavelength, okay, then it turns out that the wavelength has a distance that can be very much like the distances between atoms. Okay, so that is why it is important. So let's have a very, very quick calculation and calculate the wavelength of an electron. Okay, so let's calculate the wavelength of an electron with this formula and just give it some actual numbers. So 6.626 times 10 to the minus 34 joule times second. That is the constant of Planck. That is a numerator. Oops, very hard to draw a line. Then, of course, the mass of an electron, that is 10.109 times 10 to the minus 31 kilograms. And then V, velocity. What kind of velocity? Well, let's take a velocity, let's say 7 times 10 to the 6 meter per second, which is much less. It's still very fast, okay, but much less than the speed of light, which is 10 to the 8th. So 2 orders below the speed of light. Okay, a very typical speed for electrons in many circumstances, many relevant circumstances. So this is a relevant number. If I plug that in, you can just do it on your calculator. I find something that is approximately 1 angstrom. Okay, that means 1 times 10 to the minus 10 meters, which is approximately 1 angstrom. And this is very small, of course, right? So this is an electron that goes already pretty fast. It has a wavelength of 1 angstrom. So you may argue that is so tiny, it has no meaning, but it has meaning because that is the size of atoms, okay? And that's why it's really important, because this wavelength is comparable to the size of atoms and therefore cannot be ignored, all right? So if we go back to this picture, hopefully you can see the picture here, you see that it leads to diffraction. So if you have atoms into an atomic lattice and electrons come in, they diffract off, they behave like waves, very much so, because the wavelength is on the relevant scale, so cannot be ignored. And because of that, you get, of course, electron diffraction, and we can see these beautiful diffraction patterns from which we can calculate the locations of where those scattering centers, those atoms, are. And we can learn about the organization of matter on the atomic scale, okay, thanks to electron diffraction. So this is remarkable. This is really useful for us, of course, to study matter, to kind of have a close-up view of how atoms are organized in space. But that is a direct consequence of the fact that electrons have wave-like properties, because if they wouldn't have that, we couldn't generate these diffraction patterns like this, and we couldn't extract pictures like the picture here above. Okay, so this is a direct consequence of the quantum mechanical nature of the electron. Now, in the same way, the quantum mechanical nature of the electron is absolutely manifest in atoms, because think about it, an atom is about an angstrom or less. An electron is going to be part of that atom. Okay, so you have for the nucleus, and its electrons around it, they are confined to a space which is less than an angstrom. The wavelength of these electrons are therefore also on that scale. So the electron wave-like properties are extraordinarily manifest on this length scale. Okay, so just like the quantization of light is manifest at very low energies, single photon energies, that's when energy becomes quantized, so does the energy of electron become quantized on a very small spatial scale. Okay, and that's exactly what atoms are all about. So we cannot describe an atom without considering the wave-like properties of the electron that is captured and part of this atom. In other words, if electrons would not have wave-like properties, okay, that means that all the properties of atoms as we know them would not be valid, okay, would not be true. So we would be living in a completely different universe, in fact. But because they do have wave-like properties, we can now describe the properties of atoms precisely just because of that very fact, just because of the fact that electrons have wave-like properties. So it has a major consequence. If electrons would be purely classical particles, we could not describe the properties of atoms because they are nothing like it. Okay, so that's where it starts. We have to include wave-like properties, and we're going to see in this course how that can be done and how, based on some mathematical descriptions of these waves, we can perfectly explain the shape of orbitals and the binding of two atoms together to form a chemical bond. Okay, so that's where we hopefully will be going to in the next couple of weeks. All right, folks, that's it for today. It's 10:50. I'm getting tired. I need a coffee, and I'll leave you with that, and I'll see you hopefully on Wednesday.
Professor,
Yes.
I was wondering, like, when should we expect the recording to be up?
Say it one more time.
Like, when should we expect the recording to be available for us on Canvas?
The recording is going to be available in 1 hour. So Zoom is going to take about an hour to process, and then they're going to send me the link, and I'll post it immediately.
Oh, perfect. Thank you so much. Have a beautiful day.
You too.
Professor, I have a quick question.
Yeah.
How did you get is the speed of the velocity of an electron 7 times 10 to the 6 meters per second?
No, it could have any value below the speed of light. I just chose one, a representative value. The 7 times 10 to the 6 is a representative value for an electron in cases like, if you use electron beams, experimentally relevant conditions. 10 to the 6 meter per second is a typical value for electrons, but it could have any value. It could be going much slower, it could be going a little faster. It really depends on the situation. The maximum value, of course, is the speed of light, but in many cases, it has an energy or a speed that is much less than that. So
Okay.
I chose an arbitrary value.
Okay, thank you.
Professor, a quick question. Harkening back to the set of images you had of the interference pattern and how the least amount of energy gives still abides by a pattern, right? And I was wondering if there is a definite point in terms of scale where the quantum mechanical properties decohere, or is that just something that is not known yet?
The quantum mechanical properties decohere?
Yeah, like you get more of like a statistically significant behavior.
Okay,
versus-
so
yeah.
decoherence typically means that you have two things, okay? Two waves that interfere in a certain way, and that there's a definite phase relation between those two waves. So let's say if I have two photons, do those two photons retain their relative motion, or let's say like of a sinusoidal modulation, which is of course the electromagnetic radiation, okay? Are they moving in concert, or they're moving kind of like independently, so to speak? So if they move independently, then they decohere really rapidly. If they move in concert, then they remain coherent for a long time. Okay, so that is what decoherence means. In this particular example, what I did is I was detecting only one photon at the time. Okay, so one photon at a time. And that means that there's no other photon that is interacting with my pixel camera, the pixel on the camera. That means that there's no decoherence involved between different photons. So it takes one at the time. And that means, I just detected the total energy independent of the phase of its electromagnetic wave. Okay, so
like more like where do you get that difference in like collective behavior of different like photons or small particles?
now the beauty of that experiment is that you don't need photons to interfere with one another. It says that the photon can interfere with itself. So one photon is enough to produce an interference pattern, even though you can only detect one pixel on the camera. But that pixel only lights up in areas where the maxima are, not where the minima are. Yeah. So it is basically, it's called self-interference.
I see.
That means that the photon can sample two holes at the same time. So it's spatially delocalized, which is for us really hard to understand. For a photon, it's easy because that is what a photon is. But for us, we like to think of a photon as being localized in space, but it's not.
Oh, okay, that's excellent. I didn't recognize the subtlety of that. Thank you so much.
You're welcome.
I'll have to add to that. I mean, I think that's what was bothering me the most when you had said, "Oh, the electron went through both slits at the same time." I was kind of like picturing it in my mind, like, how is it possible for it to be, in both places at the same time if it's just localized in space, like you said, not to think about it as,
Yeah, so what holds for a photon also holds for an electron in this limit, right? And it's very hard for us to understand how can a photon, which is for us a mass holding particle, how can it sample two spaces at the same time, two locations at the same time? And the answer is that if we are considering electrons in this limit, we cannot think of it as a point in space. It is in fact a wave in space. So the spatial extent of the electron is much larger than we think it is. It's not a point in space. And it's just hard for us to appreciate that because we have a certain way we think about matter. Matter is always localized in space and has a definite mass. But here we have a situation where matter has a definite mass, but it's not localized in space. It is delocalized in space. It can sample 2 locations at the same time. It can seep through 2 holes at the same time. Or, I mean, maybe I should say it can sample them at the same time. And that is counterintuitive to us. But on that particular scale, on the scale of single photon energies, this is what the world looks like. This is just how it is. Right? So we try to kind of extrapolate that limit to the limits that we are familiar with through our own experiences, through our senses. We say, this is how the world works. It turns out this is how the world works in our limit, but in the limit that is much different from where we live, the situation is a little different. This is where quantum mechanics comes in. Quantum mechanics is a framework to describe that limit. It's different from our senses, and that's why it is difficult to understand, but also fascinating.
Right. Yeah. Yeah. I think trying to, I guess, what's the right way to say, discern, or the macroscopic world versus the, the microscopic, very, very microscopic is going to be a challenge this quarter, but I think it's going to be really interesting too.
Yeah. Great.
Professor?
Yeah.
What do you mean by sampling both holes?
Well, I mean, I use the word sampling because I don't want to say the electron goes through 1 hole or the electron goes through 2 holes, because that already forms a picture in your mind of, let's say, a mass holding particle is then kind of like going through 2 places at the same time, which is really hard for us to understand. So what I'm thinking about is the electron behaves like a wave, which is delocalized in space, okay? And it just feels the presence of those 2 holes some way, somehow. So I'm not really invoking the picture of sneaking through a hole, because that's really something that you associate with a tennis ball rolling through a hole.
Yeah, exactly. Okay.
So I want you to kind of move away from that a little bit, moving away from your own experience and thinking about it as, okay, there is a wave, and a wave samples or knows that those 2 holes are there, and it acts accordingly. Right?
Okay.
So that's just another way of describing it without invoking the picture of your own kind of like experiences in the world.
Okay, thank you.
Mm-hmm.
Can we think about it more as like a kind of like a sheet rolling through space?
Yeah, you can think about it as a wave. So the electron, you can think of it as, where is the electron? Well, the electron is now not a point mass, but it is actually a wave. So it has a kind of an extension in space. Okay. And this wave is just traveling and encountering things on its path. And it acts according to the things that it encounters, and it changes and it adjusts. And those are things that we will see. And the diffraction and the interference pattern is one of those consequences.
Okay. Sounds good. I'm just trying to picture this, or trying to understand,
Yeah, excellent.
Thank you.
All right. See you guys. See you on Wednesday.
Bye, Professor.